In this video, we are going to talk about sequentially compact sets in a metric space, together with a related property called total boundedness. So imagine that we're working in some metric space where M is the set and D is our notion of distance. A subset A is called sequentially compact if every sequence in A has a subsequence which converges to a limit in A. So here xn is a sequence. I'm omitting any enclosing brackets or parentheses there. Similarly, x sub n sub k also denotes a sequence that's a subsequence of the original sequence x sub n. So we say our set is sequentially compact if every possible sequence yields a subsequence which really does two things. So there's like two layers to this condition here. The first layer is that the subsequence must be convergent. And then the second layer is that it has to converge to a limit in A. So it's not enough to know that it converges. Its limit also must live in the set in question. Okay, let's start with these two examples. Consider first the open interval from 0 to 1 as a subset of the Euclidean real number line. Is it possible to find a sequence in this set for which there is no subsequence converging to a limit in the set? And the answer is yes. Let me give you such a sequence. Consider the sequence of terms 1 over n plus 1, generating the ordered list 1/2, 1/3, 1/4, etc. This sequence converges to 0. If the original sequence converges, all subsequences must converge, and they must converge to the same limit. So all, let me just call it like x sub n sub k, all possible subsequences also converge to 0. Since 0 is not in that set, we conclude that this open interval is not sequentially compact. Before we move on to the next example, let me make a remark, and that is that the closed interval from 0 to 1 is a bounded subset of R. I hope you studied in first semester real analysis the Bolzano-Weierstrass theorem, which tells us that every bounded sequence of real numbers contains a convergent subsequence. So when I was thinking about sequences in the open interval from 0 to 1, I had to recognize that every possible sequence would produce a convergent subsequence. So we always have this first level of the behavior that we're looking for. But since 0 is an accumulation point for the set which does not live in the set, I can create a sequence which converges to that point. That's how I was able to show that this first example was not sequentially compact. Take a moment to think about the closed interval from 0 to 1. Like the first example, the closed interval from 0 to 1 is bounded. So any sequence in this set is bounded. By Bolzano-Weierstrass, we know that any sequence in this set will yield a convergent subsequence. However, in this situation, this set is closed. So we cannot construct any kind of sequence which converges outside of the set, because if we could write down a sequence which converged to a point not in this set, that point would become an accumulation point of the set, and yet this set is closed, so it contains all possible accumulation points. All right, so I'm not going to write out a full proof here. I'll just write the brief justification. Bolzano-Weierstrass tells us that basically the first behavior we're looking for happens. Every sequence has a subsequence which converges. And then since 0 to 1 is closed, the sequential limit must be in the set. Okay, take a moment to try these two examples. The first one is what I call the Archimedean set. This is the set of points on the number line that look like 1, 1/2, 1/3, 1/4, etc. And then the second one is the set of integers. I hope you concluded that neither is sequentially compact. For the first one, it's clear what sequence to write down. How about the sequence 1, 1/2, 1/3, etc.? Again, this converges to 0, but 0 is not an element of that set. By writing down a convergent starting sequence, all possible subsequences also converge and converge to the same limit. So since all possible subsequences of this original sequence converge to 0, and 0 is not in the set, this example is not sequentially compact. With integers, we are now looking at a set which is not bounded, so I can't immediately use balls on a wire strauss. And in fact, what you might have realized is that you can easily write down a sequence for which no subsequence will converge. Try the sequence 1, 2, 3, 4, etc. It's monotone increasing without bound, so every subsequence is going to be monotone increasing without bound. No subsequence will converge. This example of the integers starts to communicate that if you want all possible sequences to have this property, then you probably need your set A to be bounded. And we will make that connection precise in a moment, but let's look at two more examples, both of which are bounded. So first, consider all rational numbers between 0 and 10, and then consider the integers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Take a moment to either come up with a sequence which does not have a subsequence converging in the set, or to try to reason that that's not possible, that every possible sequence yields a subsequence which converges to a limit in the set. All right, this bounded set of rational numbers is not sequentially compact. And here's an example. Consider the sequence of rationals 3, 3.1, 3.14, 3.141, 3.1415, etc. This is a list of rational numbers between 0 and 10, so this is a sequence in the set. However, this sequence converges to pi, which is not rational. Since the original sequence converges to pi, all possible subsequences will also converge to pi, and since pi is not a member of the set, we conclude this example is not sequentially compact. Once again, my thought process here constructing this example was I realized that pi was an accumulation point of the set that didn't belong to the set. So I constructed a sequence that converged to that accumulation point in the complement of the set. I'm not going to be able to follow that process for the second example though, because no collection of integers has an accumulation point. So if you haven't already done so, come up with an explanation for why this subset of the integers actually is sequentially compact. If you start to imagine what a sequence made up of integers between 0 and 10 looks like, well, you could have actually written one down, like 7, 1, 7, 2, 3, 7, 0, 10, 7, 8, 7, 4, etc., etc. I'm making up an infinite list from just a finite collection of elements. In order to write down an infinite list with only finitely many terms, at least one of them is going to have to be repeated infinitely many times. In this case, I was trying to clue you into that with the number 7. So actually here we have a pretty strong conclusion, which is that any finite set, a set made out of finitely many elements, must be sequentially compact. Notice here the metric doesn't even matter. In any metric space, if you are looking at a set which only has finitely many elements, then this argument must hold. An infinite list of those elements must repeat at least one member infinitely many times, producing a constant subsequence which converges to that member itself. So in my example, I was forming the constant sequence of 7, which would converge to 7, which of course belongs to the set. Okay, I have two more examples for us to look at before we switch gears for a moment. My first example is actually no longer interesting. I have markers in my room with a discrete metric. But this is a finite set. I don't have infinitely many markers, so immediately we know it's sequentially compact. What about the interval of real numbers between 0 and 1 with the discrete metric? So not the Euclidean metric, but the discrete metric. Think about this for a moment. Okay, before I tell you the answer, let me notice a couple of properties. Discrete metric spaces are always bounded, and no set in a discrete metric space has any accumulation points. So at first it seems promising, but actually this is not sequentially compact. And the reason why is that in order for a sequence in a discrete metric space to converge, it must become eventually constant. However, this set has infinitely many elements in it, which means that I can make a sequence of entirely distinct terms. Notice the sequence 1, a half, a third, a fourth, does not converge, nor does any subsequence, because no term is ever repeated. So since no subsequence is eventually constant, no subsequence converges. All right, I hope these examples gave you a working feel for what sequentially compact means. Let's take a moment now to talk about a related notion. All right, we said that if you had a sequentially compact set, it seemed like it needed to be bounded. In fact, it needs to be an even stronger form of bounded called totally bounded. So we say a set A is totally bounded if, for any choice of positive number epsilon, you can then find a finite set of points in the metric space so that A is contained in the union of their epsilon neighborhoods. In other words, A is covered by their epsilon neighborhoods. Let me sketch a picture of what this looks like. Suppose this is our set A. The way you want to read this definition is that you first pick the positive number epsilon. Think of that like a radius. So let's say this is my radius epsilon. Then once you have that radius, you can then find a finite set of points so that when you construct all of their epsilon neighborhoods, where epsilon is the same fixed radius, it covers A. All right, so say I start with this point and say here's its epsilon neighborhood. All right, I'm going to need more points because A is not just under that epsilon neighborhood, so let me pick this one. So there are two epsilon neighborhoods. Then I'm going to pick this one. Notice there I picked a point outside of the set, but that's okay. And then how about here? And here. Notice it's the same radius each time, so epsilon here is fixed. And then let's see, let me speed this up a little bit. So how about there's another neighborhood, and there's another neighborhood, and here's another one. And here's another one. Normally I'm drawing this on a chalkboard, and my neighborhoods are not quite so consistent. But they should be because it's all the same radius. So I just need a couple more. And I've now covered A. I lost track of how many points I was using, but it was a finite set. I think it actually looks like about 15 points. Here I was able to construct a finite covering of this set with neighborhoods of this radius, but had we worked with a smaller radius, we could have done something similar. So this set A actually is totally bounded. So whenever a set has this property that for any positive choice of radius that you make, you can then find a finite set of center points so that A is covered by their epsilon neighborhoods. Then we say that set is totally bounded. Totally bounded is related to our regular notion of bounded. In fact, totally bounded and bounded are equivalent notions in Rn. That was one way I knew that this set A was in fact totally bounded. If I view it as a subset of R2, it's a bounded set. But that's not necessarily true in general. The correct statement is that totally bounded is bounded. So totally bounded always implies bounded, but bounded does not always imply totally bounded. So being totally bounded is like a stronger notion. Let's prove this. Suppose A is totally bounded and choose epsilon, the radius, to be 1. If A is totally bounded, then for any choice of radius, I can then go find a finite set of points to create neighborhoods which cover A. So that's what I'm going to do, is I'm going to take this radius and then go find the points. Suppose x1 through x sub n is a finite set of points with a property. So let's say, suppose this set has the property that A is contained in the union from k equals 1 through capital N of these radius 1 neighborhoods. Choose any x in K. I'm going to show that the distance from x to this first center point x sub 1 is a bounded quantity. In my picture, imagine x1 is this first point. And let me just drop x here. In this image, it looks like x is being covered by this neighborhood and also this one. This is an illustration of this proof. Let me just pick this point. Select How about we call it x sub j from the list, so that x is in the radius 1 neighborhood around x sub j. So in my picture, maybe this point is x sub j. I think I need about one more line, so let me slide the proof up. Then the distance from x to x1, by the triangle inequality, that's less than or equal to the distance from x to xj plus the distance from xj to x1. And then that's less than 1 plus, well, since this set is finite, if I looked at all of the distances from each of these center points just up to x1, that set of distances is a finite collection of distances. So whatever the distance from xj to x1 is, it's less than or equal to the maximum of all of those distances. So how about we do the distance from x1 to x2, the distance from x1 to x3, all the way through the distance from x1 to x sub n. And then 1 is a fixed number. This set of distances is a fixed number. There's no dependence here on x or x sub j. So let's call that right-hand side our bound B. So every totally bounded set is bounded, but the reverse is not always true. You won't come up with a counterexample in Euclidean space, but see on your own if you can come up with an example in, say, a discrete metric space. All right, let's connect the two ideas that we've learned in this lecture. So we are going to prove that if A is sequentially compact, then A is totally bounded. To prove this, we will actually prove the contrapositive. So we will show that if A is not totally bounded, then A is not sequentially compact. To understand how this proof is going to go, we need to carefully negate the definitions that we have. So what does it mean for a set to not be totally bounded? Let's flip back to the definition just for a minute. We said if A is totally bounded, then for any choice of radius, there's a finite set of points in the metric space so that A is covered by their corresponding neighborhoods. If a set does not have this property, then it means that there's some radius, so there's some choice of epsilon that we can make for which there is no finite set of points generating this finite collection of neighborhoods covering the set. Okay, so that will be the second sentence of my proof here. The first is, suppose A is not totally bounded. So then, there exists some epsilon not greater than 0. It's like a bad choice of radius, so that no finite set of points creates epsilon naught neighborhoods covering A. So let me write, there is no finite set of points satisfying that A is contained in their union of epsilon naught neighborhoods. It's going to be helpful here to have a picture. So again, imagine this is A. And imagine this is our radius, epsilon naught. What we're going to do is build up a sequence. Let me show you how to choose all of the points in the sequence. Step 1 is to just choose the first element in the sequence to be any point in A. All right, so how about this one? Now let me imagine drawing the neighborhood around it with that bad radius. I know that this neighborhood does not cover A. If it did, then x1 would be a singleton set covering A with just a single neighborhood. So there has to be some of A in the exterior of this neighborhood. That means that we can make another choice of sequence point to be any point in A not covered by this first neighborhood. So I will write, choose x2 in A, take away that first neighborhood. And just as a note to ourselves, for reading this later, this is possible if A is not totally bounded. That's how we chose epsilon naught. All right, so let's say that second point is here. And then here's its neighborhood. In my picture, it's still possible to choose points of A which do not belong to either of these two neighborhoods, but convince yourself for a moment that I can keep going. So can I pick a point A out here which is not covered by the x1 neighborhood or the x2 neighborhood? The answer is yes, because if I couldn't pick another point out here, then x1 and x2 would be a finite set covering A with their epsilon naught neighborhoods. So it's like this assumption that we made with this radius means that we can just keep going. So let me pick x3 there. And here's its neighborhood. Okay, so for our third choice, similarly, choose x3 in A, take away the union of the first two. And this kind of choice is always possible. So now the sequence construction should be clear how you build up the sequence. Let me say, choose the nth term to be in the set A, take away the union of the first n-1 neighborhoods. And we can always do this. Okay, so now we have some sequence of points in A. None of these sequence terms live within each other's neighborhoods because we always pick them on the exterior. So I could pick x4 here, I could pick x5 there, but I couldn't make a choice of a point from inside of a neighborhood. So let me write, by construction, whenever the index m is not in, the distance between the x sub n and the x sub m terms is greater than or equal to this radius epsilon naught. Since the set of pairwise distances is bounded below, these pairwise distances cannot get arbitrarily close. No subsequence of the sequence can be Cauchy. And therefore, no subsequence can converge. So now we have a sequence of points in A with no subsequence which possibly converges. So if A is not totally bounded, then A is not sequentially compact. That is the contrapositive of the result that we wanted to show, so now we're done. If A is sequentially compact, then A is totally bounded. Our next topic is compact sets. It will turn out that a set being compact is equivalent to a set being sequentially compact. However, I wanted to teach sequential compactness first, because, as I hope the examples that we worked through illustrated, at this point you should have a pretty good feel for how sequences and sets can behave. Our ability to work with sequences will actually give us a good feel for what compact sets must look like. Okay, thank you for your attention.